Dear ladies and gentlemen, I am Professor Ievgen Mochalin. Now I am working for Zhejiang Normal University, College of Engineering in People's Republic of China. I am going to report the results devoted to the stability and outer oscillations of high pressure air cushion modules, which are also known as air casters. In this study, an air cushion module, the abbreviation is ACM, which is a bearing platform floating on an air film, is used to enable free sliding along a support surface floor. The concept of air cushion has been known since 1716. The idea involves supplying air under a load from a device such that the load floats above the ground and can be facilely transported. Toward the end of the last century, hovercrafts and large amphibious platforms have been well developed. They are generally called as air cushion vehicles, ACV. Their main specifics include the low cushion pressure, typically less than 5 kPa, and higher airflow rate to enable higher floating and reduced sensitivity to support surface relief. Another class of air cushion platforms, based on the ACM, has attracted considerable interest for industrial indoor transport and lifting systems. The cushion pressure and flow rate are relatively higher and low, respectively, allowing the use of air supply from conventional factory pneumatic systems, whose pressure is about 5 bar. Among the advantages of this transport approach are higher maneuverability, low specific floor load, low displacement force, and clean environment. A high pressure ACM requires the support surface to be flat and extremely smooth. A flexible elastic shell rubber bellow surrounds the cushion zone, and the minimal outlet gap height is approximately 0.1 mm. A number of companies, such as Solvin from Finland, Airgo and Air Barge companies from USA, and LKS AG, Switzerland, have proposed the development and production of industrial air cushion transportation systems. However, thus far, a theory that convincingly describes the stability of a high-pressure ACM in equilibrium state and its vertical up and down dynamics has not been reported in open literature. The vertical dynamics is important because high-pressure ACMs undergo vertical outer oscillations. This compels operators to reduce the airflow rate in the module to a minimum, thus increasing the friction force. This fact constrains the application of higher pressure ACMs. It also prevents lowering the stringent requirements of the support surface. For example, to reduce friction for moving loads on a typical concrete surface, the airflow rate must be 25 times greater than the rate required for a smooth steel sheet surface. Then the on-cushion steady state becomes unstable and vertical oscillation occurs when so large flow rate. Accordingly, in this study, an analytical model of the ACM vertical dynamics is devised. Moreover, the stability of its on-cushion steady state and its dynamic behavior when outer oscillating are investigated. Air compressibility is consistently considered not only for the cushion plenum zone, but also for the inlet and outlet flow regions. Traditional linear stability analysis is supplemented with a numerical evaluation of the nonlinear system response. This provides deep insight into a broad view of the physics of the vertical vibration of higher pressure ACMs. A typical higher pressure ACM is illustrated in Figure 1. The influence of the flexible bellow or skirt for ACVs. on the air cushion system dynamics is expected to be significant. However, the coupled processes of cushion aerodynamics, hull motion, and flexible bellow dynamics, including deformation, are difficult to describe. Accordingly, in many studies, the shape of the ACV skirt was considered to be fixed and had no influence on heave dynamics. In establishing the research objectives, assuming a simplified schematic based on the replacement of the rubber bellow by a hard sidewall as shown in Figure 2 is methodologically useful. The connection of the ACM to a compressed air source is considered according to the socket shown in Figure 3. The receiver, component 1, is charged from a compressed air network or individual compressor. The pressure-reducing valve, component 2, maintains constant pressure P sub R before the inlet of the air cushion module. The air temperature T sub R before the inlet is assumed to be constant. The throttle valve, component 3, at the inlet enables flow rate variation into the air cushion with constant supply pressure P sub R. The volume of the air cushion is component 4. The outlet gap between the rubber bellow in Figure 1 or sidewall in Figure 2 and floor is considered as a throttle orifice 5, varying with the cushion pressure P sub C. Involving the dynamics of the rubber bellow in the analytical study of ACM equilibrium stability is problematic. Therefore, at this stage, an ACM based on the schematic in Figure 2 is considered to determine the internal regularities that do not depend on the rubber bellow. Most studies on the vertical dynamics of the ACV and high load ACM are based on a mass balance equation for the air volume in the cushion and a vertical motion equation for the framework and external loading. In a general form, the mass balance equation is as follows, equation 1. The equation of vertical motion can be expressed as equation 2. Volume V sub C can be represented as equation 3. Using additional expressions for the inlet and outlet volume flow rates, equation 1 transforms into equation 4. Force balance equation at equilibrium is given by equation 5, representing the actual cushion pressure as the sum of its equilibrium value and a dynamic variation, and using equations 2 and 5 yield equation 7. The supply air density ρ sub R can be defined from the ideal gas state equation. Air compressibility certainly plays a significant role in air cushion processes, including the stability of steady suspended on cushion state. However, the nature of instability becomes clearer if incompressible flow is considered first. For the incompressible case, the density is constant. Consequently, the mass balance equation reduces to the form of equation 8. Transformations with the use of additional known gas dynamic formulae gives equation 9, which is derived from equation 8. Q sub 0 is the designation of the volumetric flow rate at the static equilibrium, and Q lowercase is used to designate the relative pressure, the ratio of pressure to the atmospheric pressure. The generalized form of equation 9 is given by equation 10 and corresponds to the free damped vibration near the equilibrium state. Equations 9 and 10 follow the natural frequency of vibration and damping ratio. In linear analysis, vertical displacements are small, hence the cushion volume change in vibrations may be ignored. The damping term in equation 9 vanishes in this case without any other changes. Thus, the ACM with a hard sidewall is linearly stable, independently on the equilibrium cushion pressure and flow rate when operating on incompressible fluid. Moreover, the damping of free vibrations is associated with a small cushion volume change due to the vertical displacement. A typical contact spot diameter for ACMs is approximately 1 meter, and the relative cushion pressure can be assessed to be less than 4. Note that when relative cushion pressure is 1.5, the loading capacity is approximately 40 tons per module. Air compressibility is a significant factor when the foregoing pressure. Moreover, the incompressible flow model doesn't display the instability phenomenon as shown above. For the cushion pressure, range and dimensions specified, the assumptions can be substantiated, which are presented in Table 1. They are: first, the aerodynamic pressures in the cushion chamber and inlet and outlet flows are adiabatic. Flow parameters variation is described by quasi-steady-state regularities. The acoustic processes in the air cushion have a minor effect on the ACM vertical dynamics. Consider the subcritical flow mode at the inlet and outlet. The parameter domain is defined by inequalities 13. For subsonic adiabatic flows, the inlet and outlet air velocities can be defined by the formulae 14 and 15. The pressure-density relationship for adiabatic gas dynamic processes is given by equation 16. Based on equations 14 to 16 and some other gas dynamic relationships, after a series of transformations, mass balance equation 4 can be reduced to the following form, equation 17. Thus, the perturbed vertical motion of the ACM near the static equilibrium position is described by a third-order ordinary differential equation. Equation 17 can be expressed in the form of equation 18. The stability of the equilibrium state can be evaluated by the Rouse-Hurwitz method applied to equation 17. In particular, the following stability condition is derived from the Hurwitz criterion, expressed by inequalities 19. When condition 13 for subcritical flow is satisfied, first and last conditions of inequalities 19 are also clearly invariably satisfied. The second condition can be reduced to the following, inequality 20. The variation in the f sub 1 function, considering different values of the relative supply air pressure and relative cushion pressure for subcritical flow, is presented in figure 4. As shown in the figure, the second condition in inequalities 19 is consistently satisfied. Thus, the final decision on stability can be made by checking the third condition in inequalities 19 based on the second diagonal minor of the Hurwitz matrix of equation 19. Substituting the expressions for coefficients s sub y from equation 17, the following form of the stability condition is obtained after transformation. Expression 21. The stability domain corresponds to positive values of f sub 2, whereas negative values indicate instability. The graphs of f sub 2 variations for several values of parameter H over delta sub 0, the relative cushion height, are shown in figure 5. The parameter domain corresponds to the subcritical flow at the inlet and outlet. Based on the results presented, a stable static equilibrium is only possible when either cushion pressure approaches to the atmospheric pressure or cushion pressure approaches to the supply pressure. Moreover, the lower the value of relative cushion height, the more stable the ACM floating state, because the typical outlet gap for higher load ACMs is approximately 0.1 mm and low cushion pressure is not used. A high pressure ACM can be considered unstable with regard to small perturbations of the static equilibrium, except for the case in which cushion pressure approaches the supply pressure, high pressure stability zone. For hovercrafts and large low pressure amphibious platform, the results indicate that a stable on-cushion position can be obtained because acceptable combinations of cushion pressure, supply pressure, and relative cushion height, whose values correspond to those in the stability regions of the graphs shown in figure 5, can be selected. The ACM becomes unstable due to the negative value of the second diagonal minor of the Hurwitz matrix, indicating that the instability is an oscillatory type. This instability is manifested as vertical vibrations with increasing amplitude. This is consistent with real observations. In a study of the vertical dynamics of an ACV near an equilibrium position, the outlet flow rate variation due to the changes in the outlet surface area is usually neglected. Only the change in flow rate due to the pressure variation in the cushion is considered. The low ACM vibrations can be similarly analyzed. Using these assumptions gives equation 22 instead of equation 18. After integration, equation 23 is derived. Equation 23 denotes the free damped vibration near the equilibrium state. It is analogical to the case of incompressible air treatment. This contradicts the results indicating the instability of the ACM in most of the possible parameter combinations. Nevertheless, the frequency and damping ratio for the oscillation can be defined by equation 23 and then compared with the result of the case involving incompressibility. For the frequency, equation 24 is derived and the damping ratio is defined by equation 25. The graphs of the vertical oscillation frequency for the compressible and incompressible flow treatments, defined by equations 24 and 11 respectively, are shown in figure 6. In the compressible case, frequency depends on relative cushion height, and in both cases, frequency depends on the gap height, delta sub 0. In comparing the data shown in figures 5 and 6, the compressible and incompressible calculation methods yield the same oscillation frequency when the parameter combination corresponds to the stability boundary, zero value of f sub 2 in figure 5. This follows from intersection of lines 2 and 3 as well as lines 5 and 6 in figure 6. Moreover, the more stable the equilibrium state, the larger the difference between the compressible and incompressible frequency estimation. In the unstable domain, the definition of oscillation frequency is not valid without further analysis. Thus, neglecting the compressibility of the cushion plenum leads to errors in the estimation of the vertical oscillation frequency by up to 40%. The graphs for damping ratio based on equations 12 and 25 are presented in figures 7 and 8 for several values of defining parameters. From the graphs in figures 7 and 8, it follows the different trends in the perturbed vertical motion of the ACM, underdamping and overdamping when cushion pressure approaches atmospheric pressure and supply pressure within low pressure and high pressure stability zones. Based on more consistent compressible flow consideration, the ACM equilibrium is unstable except when the cushion pressure is extremely low or approaches the supply air pressure. Thus, the analysis shows that for an ACM without a rubber bellow, oscillatory damped perturbed vertical motions when cushion pressure is less than 1.05 and aperiodic damping motions when cushion pressure approaches the supply pressure are possible. The foregoing consideration indicates that for an ACM with a hard sidewall, stable equilibrium is possible in a narrow area of the parameter domain. In contrast, in most areas of the domain, oscillatory instability exists with increasing initial small perturbations, including vertical displacement and cushion pressure variation. Therefore, a study of the finite amplitude vertical motion of the ACM without assuming small values in the dynamic variations of all equilibrium parameters is significant. This results to a nonlinear problem formulation, which is considered further. The stability results of this study are in full agreement with earlier observations reported in open literature with respect to ACVs for applications in which cushion pressure is low. Therefore, the stability results of the current study are compared with the experimental values of Sweet et al. In terms of the typical operational parameters of ACV. The air cushion configuration, including the constant supply pressure provided by a large external reservoir, considered by Sweet et al., is similar to that examined in the present study. The comparison results in terms of f sub 2 function is presented in Figure 9. Based on the data in Figure 9, the theoretical estimation of the stability boundary is adequate for the actual process. The present analysis is anticipated to be adequate for the higher pressure ACM because it comprehensively accounts for the air compressibility in modeling the cushion area processes as well as the airflow into the cushion and through the outlet gap. In a nonlinear study, a simplified ACM schematic with a hard sidewall is considered. One of the main specific features examined in the finite amplitude ACM motion is the possibility of the outlet gap closing when the sidewall touches the ground. A convenient and feasible case of a sliding sidewall is considered, as illustrated in Figure 10. The design allows the frame to continue moving after the bottom of the sidewall touches the ground. In the first approximation, the friction force between the sliding wall and guide is neglected, resulting in zero reaction force. The mass conservation equation can be rewritten as follows, equation 26. Motion equation 7 can be rewritten as equation 27. The cushion dynamic pressure variation is not considered to be a small quantity, and relative pressure formulation is still applied. Motion velocity can be denoted according to equation 28. After transformations allowing for the model specifics, the mass conservation equation 26 takes a form of equation 29. Equations 27 to 29 comprise an ODE system, which can be integrated numerically using appropriate initial conditions. Some results in the form of responses of the cushion dynamic pressure and ACM vertical displacement are presented in figures 11 and 12. The selected initial perturbation is the pressure rise, which corresponds to 0.1% of the atmospheric pressure. The results of the nonlinear dynamics fully correlate with the linear analysis data. In particular, small initial perturbations are observed to diminish when cushion pressure approaches the atmospheric pressure or it approaches to the supply pressure. For example, both linear stability analysis and finite amplitude motion analysis predict the low pressure and higher pressure stability boundaries in good correlation. The finite amplitude behavior of the system near the stability thresholds agree with the linear analysis prediction. Based on the linear theory, there are damped perturbed oscillatory motions when cushion pressure approaches the atmospheric pressure and aperiodic damping when cushion pressure approaches the supply pressure. The results for higher cushion pressures are given in figure 12, which support the same trends. Near the linear stability boundary, the increase in perturbation amplitude plateaus at some level. However, the farther the distance from the stability boundary, the greater the dynamic pressure and displacement amplitude. The upward ACM vertical displacement becomes equal to the height of the cushion plenum H. Seemingly, the module jumps with the load. Note that the amplitudes seem to increase with time. However, extremely large amplitudes of pressure variation and vertical oscillation are not possible. Hence, the maximal values of the vertical displacement and cushion pressure oscillation amplitudes are expected to be lower than those predicted by simulation, first of all due to damping. The vertical motion of ACM is periodic. In this regard, an interesting question is how the frequency of finite amplitude oscillations correlates to the frequency defined by linear analysis. As it was shown, the stable oscillatory motion shifts to oscillation with the increase in amplitude as cushion pressure exceeds the stability threshold near the value of the atmospheric pressure. This is fully confirmed by the nonlinear analysis. The frequency amplitude characteristics of relative vertical displacements obtained using the discrete Fourier transformation of y of t, the vertical displacement, correlation, are shown in Fig. 13. The parameter combination is selected which is suitable to reflect typical system behavior beyond the linear stability threshold. Different time frames are considered to determine the possible evolution of dominant frequency with time. In each of the three characteristics shown in Figure 13, the first peak is observed at zero frequency. This corresponds to a constant shift of the span center from the equilibrium position, y equals 0. The shift increases with time, as reflected by the increasing amplitude in the first peak with time frame length. The second peak on each graph corresponds to the main oscillation frequency. Initially, the oscillation frequency, which is obtained by numerical integrating the governing equations, approximates the linear analysis prediction. However, the oscillation frequency approaches a lower stable value with increasing amplitude. After the second peak, the subsequent decreasing peaks corresponding to multiples of the main frequency are observed at time frame length ½ second and 1 second. In the model considered above, no energy dissipation mechanisms are involved. Hence, the displacement amplitude can considerably increase to higher ACM jumps, which are barely feasible. Thus, analyzing the influence of damping mechanisms has practical significance. For instance, a resistant force, which is proportional to the vertical velocity and acts when the sliding sidewall is in contact with the ground, can be facilely introduced into the model. This idealization is consistent with the effect of the rubber bellow and the deformation of the sidewall when it touches the bearing screen. The incorporation of the resistance force into the vertical motion equation transforms it into equation 30. With increasing amplitude, a notable qualitative effect is observed. The greater the damping coefficient, the lower the amplitude, and the faster the amplitude stops to increase. The model assumptions indicate that the cushion pressure cannot decrease to less than the atmospheric pressure. Nevertheless, it can increase when the outlet gap closes. Therefore, the pressure peaks can increase considerably when damping is relatively low. However, the magnitude of pressure increase may be less than the magnitude of decrease when the damping coefficient is high. This is because the resistance force only acts when the outlet gap is closed and impedes the downward motion of the module, thus limiting the increase in pressure. The fundamental conclusions are as follows. The ACM facilely becomes an outer oscillation system when its working pressure increases. Moreover, the vibration and cushion dynamic pressure amplitudes may be extremely high. The main reason for the instability is the air compressibility in the cushion chamber, and the relative cushion height significantly influences the stability boundary. The most stable operational modes enabling higher lifting are those whose cushion pressure approaches the feed pressure. This is demonstrated to be true for the subcritical airflow throughout the cushion domain. It must be checked when flow at the outlet gap is critical. Throttling at the inlet destabilizes the ACM with respect to vertical vibration. An acceptable value of module oscillation amplitude can be achieved at any cushion pressure magnitude by introducing sufficient damping. The results obtained provide insight into the occurrence of instability and specific features of the vertical vibration of ACMs with high loads. The data also extend the design database for the practical development of air cushion cargo transport systems. Thank you for your attention.